We continue to learn Chapter 4, Linear Transformations. Section 2, Matrix Representation of Linear Transformations. Part 3, Matrix Form of LA from Rn to Rm using general basis. We first see this theorem, 4.2.3. Let E composed by U1, U2 till Un, and F composed by B1, B2 till Bm be ordered basis for Rn and Rm respectively. If L, this is mapping Rn to Rm, is a linear transformation, and A is a matrix representing L with respect to E and F, then we have this relation that J's column for A equals B inverse times LUJ for J varies from 1 till N, where B is obtained by B1, B2 till Bm as its M column vectors. Okay, by theorem 4.2.2, we know that the J's column for A of this matrix representing L should be LUJ. So this mapping of L function on UJ on the basis vector of the original vector space, right? LUJ with respect to F for J varies from 1 to till N. Now we see the proof. If A is representing L with respect to E and F, then for J varies from 1 to N, we have LUJ equals A1J times B1 plus A2J times B2 plus till plus AMJ times BM. So it equals B, this matrix composed by B1, B2 till Bm times AJ, the J's column vector. And then in order to get AJ, we can just use the inverse matrix of B. So AJ equals B inverse times LUJ for J varies from 1 to N. Okay. From this theorem, we can easily have this corollary. If A is a matrix representing the linear transformation L from Rn to Rm with respect to the basis E composed by U1, U2 till Un, and F composed by B1, B2 till Bm, these column vectors, then the reduced row echelon form of this augmented matrix, the left part is B1, B2 till Bm, the right part is just LU1, LU2 till LUN, is IA. This means if you transform this part, the augmented matrix, this part, to be identity matrix, the right part, this part, immediately comes to A, right? Becomes A. We see the proof of this corollary. Let B equals B1, B2 till Bm, this matrix. And then we know if you write this augmented matrix here, if you transform the left part to identity matrix, then the right part is just B inverse LU1 till B inverse LUN. And we know B inverse LU1 just is the first column of A, okay? And B inverse LUN is just the nth column of A. So we have this one. If you want to compute the matrix representing the linear transformation L, you can just write the augmented matrix and transform the left part to identity matrix. The right part is just A. Let's see this simple example. Let Lx be defined in this way. Find the matrix representation of L with respect to the ordered basis U1, U2, and B1, B2, B3, where U1 is here, U2 is here, and B1, B2, B3 given here. So, in order to find the matrix representation of LA, the matrix A, so we will consider to perform this mapping on the coordinate vectors of the original vector space first. So you will consider LU1 and LU2, right? And note that LU1 and LU2, if you do this mapping, the vector you obtained in fact are the coordinate vectors with respect to the standard basis, not the basis here given you at B1, B2, B3. You need to transform this coordinate vector to this basis. So you can consider the augmented matrix. The left part should be B1, B2, B3 composed by these basis vectors, and the right part is just LU1, LU2. Okay, so we write like this. We first compute LU1 here, LU2 here, and then you write this augmented matrix. You transform the left part using the 3 types of row operations. You will get here. The left part becomes identity matrix. The right part is immediately the matrix representing L with respect to this given basis here. So the matrix representing L with respect to the given ordered basis is A, which is first column minus 1, 4, minus 1. The second column is minus 3, 2, 2. At last, we mention some application in computer graphics and animation. In computers, a graphic object can be represented by its vertices and the implied connections between these consecutive vertices. For example, a triangle with vertices 0, 0, 1, 1, 1, minus 1 can be represented by this matrix T, from 0, 0 to 1, 1 to 1, minus 1 to 0, 0 again. Okay. And then, for example, if we do this mapping, L of x equals x plus a, this means you move the original triangle to a new position. This is a translation, right? Translation from origin to A. But this mapping is not linear mapping. This is not linear transformation. You can show easily that, for example, L times alpha x equals alpha x plus A, which in general does not equal to alpha times L of x. And this one, we write this animation as L of x equals c times x. If c greater than 1, so means you enlarge this triangle. So this is a dilation. Okay, and you can also use this matrix times x. This matrix is minus 1, 0, 0, 1. So if you have this matrix times x, this means for the first component of the new vector, which is the negative value of the original first coordinate. Okay, and x2 keeps unchanged, so should be a reflection with respect to the x2 axis. This one is a linear transformation. Okay, and also rotation we mentioned before, right? If you use this matrix, cosine theta, sin theta, first column, second column minus sin theta, cosine theta. So this matrix times x means you rotate each vector anti-clockwise by angle theta. So this one is for rotation in the animation.